everybody, how's it going? Today we're going to be talking about electric flux and Gauss's law. Flux is defined as the rate of flow across a given area. So we can define the electric flux mathematically as capital Phi. It's denoted as capital Phi. The flux is the double integral across the surface S. This is what the subscript S means. Across the given surface, E electric field dot dA across the given area. So this expression for the electric flux can be reduced to phi equals the electric field times the area. And this little subscript on the electric field means it's perfectly perpendicular to the area it's traveling across, the electric field. So if we have some sort of ring, and let's say the electric field is going through it, the electric field is perpendicular to this ring or whatever area you are working with. So if you're not perfectly perpendicular, we have an expression phi as E a cosine of the angle with respect to the vertical. So if we have our charge, or our ring, tilted to the vertical, this angle right here is theta. So now we have our electric field lines going through this ring. This theta right here, cosine theta, is this angle now with respect to the vertical of the electric field. So now we move on to saying why the electric flux is important. Like, why do we give a flux? So it becomes very important in the finding electric fields and the formulation of Gauss's law, which is our next subject. So another helpful thing to think about with flux is, like, if you have a fishnet and you dumped it in the water flowing through the fishnet would be a measure of flux, because it's the rate of the water flowing through the fishnet. If we have a Gaussian sphere, or the Gaussian surface of a sphere, we have it as our flux as E. We take it outside the integral dA, and we put this little circle around the two integral signs to mean it's a closed surface, dA, and then we get this expression for through a closed sphere, epsilon naught r squared dA. So we can substitute in the electric field, which we found, which we know from earlier, like finding the electric field of a particular charge. And we have this expression given to us. And so now we take this. So we have, I'll write it again, have our expression as Q 4 pi epsilon naught r squared, the integral of dA. And so this r squared denotes the radius of a Gaussian sphere, and the integral over a closed surface dA is just the area. And the area of a sphere is 4 pi r squared. So we can plug that into this expression. 4 pi epsilon r squared times 4 pi r squared. We reduce, and we're left with the flux given as Q over epsilon naught. And let's just pause right here for a moment. This is a huge result that we're given here. The flux is the charge per the constant, the permittivity of free space. So we have this expression, and this expression for the flux applies to any closed surface that we're given. And so now if we substitute back in over here our expression for the flux, we have the double integral of E dot dA equals Q over epsilon naught. And this can be generalized to multiple point charges. So you can sum this up over, if you have like say 7 charges, you have 7 charges added together divided by your permittivity of free space. So now this result leads to the biggest, one of the fundamental equations in electromagnetism, which is Gauss's law. And Gauss's law is one of the 4 fundamental Maxwell equations. So this right here gives us Gauss's law. And let me just write it a slightly different form. We have our electric field dot dA equals capital Q over epsilon naught. And this is Gauss's law. And once again, this is a big deal because it's one of Maxwell's 4 equations, and this applies to a wide range of cases, especially when you have symmetry in a problem, when you're working with spheres, cylinders, lines, sheets, anything of that nature. We can use this to find the electric field. And it's really important because it tells you the electric field, the source of an electric field is the charge. And so it's just proportional to the charge divided by a constant, integrated over an area. So now we have, so let's use an example. Say we have the case of a line charge. And we want to find the electric field E. So we have the, this has a positive charge density of a line charge of a lambda. So now we think about what would be the best surface to enclose this line of charge. If you think about a line, it'd be a cylinder, right? So we have this cylinder, and it encloses a line of charge through it. So, or if we orient it slightly different, we can say the sphere looks like this along the z-axis, and the wire goes through it. So since the sides, we have to find the electric field on each surface of the sphere. So the surface of the cylinder, excuse me. So the surface of the cylinder has a side wrapped around it, and it has a top and a bottom. So our flux, finding the flux, is going to look like this. We have the integral of the top, E dot dA, plus the integral of the bottom, E dot dA. And we plus the integral of the side, E dot dA. And because these top and bottom ones are along the same direction of the line of charge, both of these become 0. So we're just left to find the side that wraps around perpendicular to the flow of charge, the line charge, lambda. So we have this expression for our cylinder, our Gaussian surface, as phi equals E, pull the electric field out of the integral dA. And we know what the area of this side is. So this would be the circumference wrapped around times the height of the cylinder H. So we have E 2 pi r H equals, so this expression equals E 2 pi r H equals Q, our charge, over epsilon naught, which is Gauss's law. So doing a little more rearranging, we find that the electric field dividing over the 2 pi r H, we find it as, first we substitute in Q, and Q in this case is the charge density, lambda, times H. We can substitute that in, and so we're given, if we substitute this in and divide 2 pi r H on the bottom, we have lambda over 2 pi epsilon naught r. And this can be applied to spherical shells. We did it for the case of a cylinder, but it can be applied to spherical shells, planes of charges. If you have a plane that's a sheet of a charge, it can be applied to all sorts of these things. And experiments testing the inverse squared dependence, which appears in Coulomb's law, and Gauss's law follows from Coulomb's law, have been tested by a bunch of people. It's been tested by Robinson, Coulomb himself, Maxwell, and others. So this is a very experimentally confirmed law, and that's why it's called a law instead of a theory. Theories are proven as well, obviously, but this has been around for centuries, and people have tested it with various amounts of experiments, and it's been tested to a great amount of precision as well. So this is one of the fundamental expressions in electromagnetism. I hope this video helped you gain a deeper understanding of electric flux and Gauss's law. And if you like this video, hit the thumbs up, and I'll see you all next time.